Hello, and welcome to a lecture on unilateral design of amplifiers. I'm Steve Ellingson. Here's an overview of this lecture. First, I'm going to say a little bit about the TPG, the transducer power gain, for unilateral two ports, and then the maximum unilateral TPG. From there, I'll discuss the unilateral design method for achieving a specified gain from an amplifier. And that will involve a technique known as unilateral gain circles. I'll talk about approximately unilateral design. This is an approach that allows us to use the unilateral design technique even if the amplifier is not strictly unilateral. And that will entail evaluation of a figure of merit known as the unilateral figure of merit. And then finally we'll do an example to demonstrate all of these concepts. So recall that the transducer power gain for a two-port, regardless of whether it's unilateral or not, looks like this. This is the general expression given in terms of the S parameters, the source impedance, and the load impedance. A unilateral two-port is one for which the intrinsic reverse gain, that is S12, is equal to 0. And in that case, we can substitute S12 into the above expression and get a simplified equation that applies just to unilateral two ports. And in that case, we have this expression. So we refer to this expression as G sub T U, where U refers to unilateral. Now, as I pointed out, this gain, whether it's a transducer power gain in general or for unilateral two ports, involves the forward gain, the intrinsic forward gain. And then we have these other two factors. We have one factor here which depends on S11 and the source impedance. So that is clearly representing the effect of the impedance terminating the input. Similarly, we have over here a factor which depends only on S22 and the load impedance. So clearly that's representing the effect of the impedance terminating the output. Now the maximum TPG for a unilateral and stable two-port. Well, I've written here the transducer power gain for a unilateral two-port that we just derived. And we know that if it's stable, then the maximum gain is achieved by simultaneous conjugate matching, as we've discussed many times now by this point in the course. In this case, it's pretty easy because gamma sub S conjugate equals gamma sub n, and here's gamma sub n from one of our very early lectures on two-port theory. And in this case, that's just going to be S11. The reason being that S12 is 0, so this whole term is 0. So summarizing, the conjugate of the source reflection coefficient is going to be S11, or said differently, gamma sub S equals S11 conjugate. Similarly, the conjugate of the load reflection coefficient is just the output embedded reflection coefficient, and that's given by this expression. And S12 is 0 for a unilateral two-port, so this whole thing is 0 for a unilateral two-port, leaving just S22. So here we find that gamma sub L is just S22 conjugate. So you can see from these two expressions that we really like it when two ports turn out to be unilateral, because then simultaneous conjugate matching becomes very simple. Now, if we substitute these expressions to figure out what the maximum TPG is, then we get this very simple expression for the result. This is, once again, the transducer power gain for a unilateral two-port, which has been maximized by simultaneous conjugate matching. We get simply that it is the intrinsic forward gain, and then a factor which depends only on S11, and a factor that depends only on S22. So we can take advantage of this factorization of the transducer power gain and write this in terms of these factors as shown here. The factor G sub 1 is this one, and we can refer to this as an input mismatch factor because it's describing the effect of the input mismatch on the total gain. Similarly, we can describe this factor using G sub 2, the variable, and calling that the output mismatch factor because that describes the effect of the output mismatch, Z sub L, S22, on the transducer power gain. And then this thing is a constant with respect to the source and load impedances. It's an intrinsic property of the two-port, so it's a constant, and we call that G naught here. So now I'd like to talk to you about unilateral gain circles. Recall the topic of gain circles has come up before in the context of available gain, where we had available gain circles. Well, unilateral gain circles are very similar. Here we're making a map, and this could be the Smith chart, a map of the real component of gamma sub s and the imaginary component of gamma sub s. And it turns out that the locus of points that have constant input mismatch factor, or constant G1, is a circle. So once again, we find that the locus of all possible values of something in this domain is a circle. Similarly, the locus of possible reflection coefficients for the load, which yield constant G2, is also a circle. And as you might now at this point anticipate, we can figure out what the centers of these circles are. We're going to call them C1 and C2 respectively, and the radii of these circles, R1 and R2 respectively. So here's how we do it. First, we define this parameter little g sub 1, which is G sub 1, big G sub 1, times this factor 1 minus the magnitude of S11 squared. Given that parameter, the center of the unilateral gain circle for the input is given by this expression, which depends on G sub 1, S11, and that's it. And similarly, the radius of that circle is given by this expression, which depends on G sub 1, S11, and that's it. Similarly, for the output situation, we can define this parameter little g sub 2, which is defined as big G sub 2, the output mismatch factor, times 1 minus S22 magnitude squared. And given that, we have analogous expressions for C2 and R2. So how do these work? Well, once again, I'm showing you the Smith chart domain. Here's the real part of gamma sub s, the imaginary part of gamma sub s. Here's a circle of constant input mismatch factor. As we consider increasing that mismatch factor, in other words, making the gain higher and higher, we find that we get circles which are smaller and smaller and eventually converge to a point, and we know what the location of that point is. That's just the conjugate of S11. How do we know that? Because we know in advance that this is the value that will result in a simultaneous conjugate match, or at least a conjugate match at the input. So G1 is maximum when gamma sub s equals the conjugate of S11. And the situation is exactly analogous for the output gain circles. So here's a unilateral design procedure. First, check the intrinsic stability of the active two-port. This is exactly the same considerations we had for the available gain technique and the operating gain technique. So check for unconditional stability first. If it's not unconditionally stable, I would suggest not using this technique. Make sure the two-port can deliver the specified gain. Once again, there's no point in trying to achieve a design in which the specified gain is greater than the maximum gain. In this case, the maximum unilateral transducer gain. Then distribute the specified gain between G1 and G2. This is your choice, and this is one of the nice features of the design. You can independently design the input and output, and that's for sure one of the reasons why we refer to this as unilateral design. What we do with the input does not influence the output. Construct the associated gain circles using the equations I just showed you. Select source and load reflection coefficients, and as always, those represent impedances, so you calculate those. And then finally, check your answer. Make sure you get the expected result using the general TPG equation. This procedure is not complicated, but it does have a lot of steps and some formidable calculation. So make sure when the smoke clears that the result you get checks. And the way you check it is by substituting the source and load reflection coefficients that you get back into the general TPG equation. So before I show you an example, I want to say something else about this procedure. The procedure assumes that the two-port's unilateral, but no active two-port in practice is exactly unilateral. However, we can still employ this technique in some cases, and this is referred to as approximately unilateral design. So, unilateral design has many advantages, so it's tempting to use this even if the active two-port is not exactly unilateral. And it begs the question then, how large is the error in this technique if one uses unilateral design even if the two-port is not strictly unilateral? In other words, even if the two ports S12 is not exactly 0. Well, the answer to that question is given by this thing called the unilateral figure of merit. And we refer to this using the variable little u. And you see this little u is function just of S parameters. So if we know the S parameters, we can calculate this little u, and that's the unilateral figure of merit. The way it works is that we can use that to calculate the associated gain error. And the way we characterize gain error is as the ratio of the actual transducer power gain to the transducer power gain if we assume it's unilateral, or if it actually is unilateral. So this is the actual TPG. This is the TPG that you are assuming by assuming that it's unilateral. So this is a measure of the error, because if it's exactly unilateral, this should be 1. And if it's not unilateral, you're going to get something different from 1. And it turns out, if you know the unilateral figure of merit, then the bound on this number, which again is nominally 1, but it's going to be different from 1 if you assume it's unilaterally incorrect without it actually being unilateral, is going to be in this range. So here's the procedure for approximately unilateral design. First, again, check that the active two-port is unconditionally stable. Confirm that S12 is small enough that this approach is going to be reasonable. You do that using the unilateral figure of merit, as I just showed you. You identify sets of impedances that yield specified gain, assuming the two-port is exactly unilateral. In other words, you just use the exactly unilateral procedure. You select impedances, and then you consider the gain and the ease of implementing the IMN and OMN. So let me show you an example. This is the exact same example as in the previous lecture, and so it might help if you have forgotten that lecture to go back and just briefly review that to see what happened there. In this example, we've got a 50 ohm input specified, a 50 ohm output specified. Here are the S parameters of the active two-port of the transistor, probably in this case. Here is the reference impedance, no surprise, 50 ohms. Here is the frequency we're going to calculate this at, and this is a bipolar common emitter transistor. The desired TPG is 15.2 dB at 1.5 gigahertz. In the available gain problem, it was actually 14.1 dB. So the goal will be a little bit different here. Now, in that previous example, we already computed stability. We found it was unconditionally stable at this frequency with a maximum available gain of 17.1. So we know that we are going to be able to achieve this gain because it's less than the maximum available gain. In this problem, we're going to design the appropriate IMN and OMN. We're going to stop short of bias integration, exactly as we did in the available gain example. So first, since this is not exactly unilateral, S12 has a magnitude of 0.02, we should assess the unilateral figure of merit and see what our likely error is going to be. So here we're calculating the figure of merit. I get a value of 0.037. Alone, that doesn't tell you much, but you use this relationship to see how the gain is going to be bounded. I find that, once again, the nominal value would be 1, that is 0 dB, and the bounds turn out to be down by 0.3 dB and up by 0.3 dB. That's a total uncertainty of about 0.6 dB. In other words, about 0.3 dB on either side of whatever the actual transducer power gain is. So in most problems, 0.3 dB is a pretty minor error, so we would probably feel comfortable proceeding with the unilateral gain technique given this outcome. You determine the maximum unilateral gain. Once again, that's this thing, given by this expression. Here we find that G1 is 4.4 dB. The intrinsic forward gain, that's just the magnitude of S21 squared, is 12 dB. And G2, the output mismatch factor, is 0.2 dB. And so the maximum unilateral transducer power gain is 16.6 dB. Now that's greater than the 15 dB or so that we had specified, so we know we can achieve the specified value. One way to do that, just one possible choice, is to make the input mismatch factor 3 dB, that's down from 4.4, to make the output mismatch factor 0.2, keeping it the same. And we can't do anything about G0 because that's just the intrinsic forward gain, so that's 12 dB. If we make just this change, then we get the specified gain of 15.2. And I'll emphasize, this is just one possible choice. There are a continuum of solutions here, which is great news because every one of those possible solutions is a different matching network, and so I'm more likely to find a matching network that has all the features that I might want as part of the actual design I'm doing. Okay, so proceeding with the choice that I made on the previous slide, here's little g1. It's given by this expression, and I get 0.715. So the center of the unilateral gain circle is here. The radius of that unilateral gain circle for the input is 0.234. And here's a picture. So once again, we are in the Smith chart domain. This is imaginary versus real component of the reflection coefficient. Here's our unilateral gain circle. The center of that circle, as always, is S11 conjugate, or that's where this would all converge if we gradually increased G1. The way to pick a value here from this continuum of possible solutions for gamma sub S is the same trick I used in the available gain technique. If I just need a quick and dirty choice from the circle of possibilities, I can employ this expression, which gives me this point here. It's the point that has the minimum magnitude reflection coefficient on the circle, on the unilateral gain circle. So this just happens to be easy to compute. It has no particular merit with respect to any other point. It's just a quick way to get one point off this circle. Of course, another strategy would be to pick some point off the circle which has some specific advantage. All right, so specific advantages we might look for are, for example, can we find a point there that corresponds to an input matching network that requires only a single reactance? That would reduce the complexity and parts count and so on. Maybe we can find a point that refers to an input matching network that has desirable reactance or stub length values if I'm doing a single stub match, for example. So this is usually the strategy that's used, or some combination of these things. But again, just to get the solution moving here, I'm going to pick off this one point. So finally, I note that independently of what I've chosen for the source, the load is set. And the reason the load impedance is set is because I chose not to fiddle with that. I just left it at the value which yields the maximum output mismatch factor. So that's just setting gamma sub L equal to S22 conjugate, and I'm just showing you where that is in the Smith chart domain here. I'm going to check my work. Here is the general TPG expression, the most general one I have available, making no assumptions. I've substituted these values of gamma S and gamma L that I've gotten through the unilateral gain procedure. This gives me 15.3 dB. That's not 15.2 dB. That's 0.1 dB greater than what was specified. So at first it appears there's some error there, but we were expecting that. We were expecting that because the error, which was indicated by the unilateral figure of merit that we computed, was plus or minus 0.3 dB. So no surprise, it's a little bit different from what we specified. We knew that that was likely to happen. And it's within the bound that we computed earlier. Finally, we determine input matching network and output matching network impedances, and then proceed to synthesize the networks themselves. We convert to impedances from reflection coefficients in the normal manner. Here's gamma sub s converted to z sub s, we get this value. Here's gamma sub l converted to z sub l, we get this value. These are both complex values, as is usually the case, so we're going to end up doing some complex to real matching here. So from this, we have everything we need to synthesize the matching networks. For the exact same reasons as in the available gain example from a previous lecture, I'm going to do this in strip line because we're at 1.5 gigahertz. I will not go through the details of that synthesis. I'll leave this as an exercise for you. I'll simply show you the result that I get. So here is the result. Here's my common emitter transistor with the bias interfaces indicated. Here is my input matching network. Here is my output matching network. I've indicated here the lengths of the transmission lines that are required. This one's open circuited, this one's short circuited. Because this one is short circuited, I have to put some kind of isolation up here, or at least indicate that I'm going to need some isolation up here. And those considerations are the same considerations that we encountered in the available gain example. And I'll just remind you that this is pretty small because one wavelength at 1.5 gigahertz in FR4 is about 10 centimeters. So this thing is just a couple centimeters in dimension. And you can see the previous example, again, the available gain example, about how I chose 1 nanofarad as these capacitor values. And then once again, I will implore you to confirm the solution. In other words, check that this is a proper solution by starting with this input impedance, adding the impedance of this thing in series, working out the stub impedance, combining those in parallel, and making sure that's 50 ohms. Again, you should be doing this many times between now and the end of the course. Write up a little MATLAB script to do this, or a little chunk of spreadsheet to do this, and confirm for yourself that the solution works. This concludes this lecture on unilateral design of amplifiers.